All right. So today we're going to do problem 2332, the latest time to catch a bus. All right. Coincidentally, this is a palindrome. If you don't know what a palindrome is, it's unrelated to this problem, but it's definitely one of those fundamental sort of questions. So just a little bit of an Easter egg, unintentional Easter egg within this problem, I guess. And before I even describe this problem, I'm going to just quickly go over the core concepts that are related. And then as we discover those core concepts, I'll just make a note of that. But basically, this problem consists of three major parts, okay? There's sorting. This will be very easy to understand, meaning this idea will become very clear, and you'll understand that we need to use sorting to solve this. There's a greedy approach to this problem. Greedy approaches are just sets of problems where, you have a situation where you always choose, what's best in that moment, right? Just greedily pick things that are best, and that'll result in the best result as a consequence. And I guess the last part is simulation, okay? Simulation is where, you're given a scenario, and a scenario has a set of conditions. And with those set of conditions, you can run through the scenario, and usually you can determine something about the game given the set of conditions, right? So in this problem, if we take the system, we sort it, and we simulate through the conditions that were set, we can greedily pick what's the best answer. Okay. So with that said, let's go ahead and read the problem. Okay, so you're given a zero-indexed integer array buses of length n, where buses I represents the departure time of the ith bus. You're also given a zero-indexed integer array passengers of length m, where passengers j represents the arrival time of the jth passenger. All bus departure times are unique. All passenger arrival times are unique. Okay, you're given an integer capacity, which represents the maximum capacity of the bus, right? So the maximum number of passengers I can get on each bus. Okay, so you're gonna have a bunch of buses. In my country, I don't know about your country, but in my country, school buses are yellow. Okay, and we'll just say that we're gonna draw a little bus. All right. Now let's say we can fit people in all of these slots. All right. Kind of packed in there, but we would say that, this bus has capacity 4. Okay, so there's going to be a bus with each bus has the same capacity. All right, so, something like this. This would be our capacity going across here. Right, so in this example, capacity equals 4. You're going to have more than one bus, right? So on and so forth, right? And each bus has a unique arrival time, and there's going to be n buses. All right, so the amount of buses here is n. Just trying to give you a little bit of a visualization here. And then you have m passengers, right? So you have passengers that are coming, this situation is pretty intuitive, right? I mean, we've all probably taken the bus at least once in our life, unless we're like some sort of aristocrat or something, right? So these are the m passengers that are waiting to take the bus, right? So in this scenario, you have m people that are going to wait for n buses, and each bus has a capacity, right? In this example, there's a capacity 4, right? And all buses have that same capacity. It's not like each bus has varying capacity or whatever. All right, represents the maximum number of people that can get on each bus, okay? When a passenger arrives, they'll wait in line for the next available bus, okay? So as you arrive, you get in the line, right? So that's pretty intuitive, right? If I got here before you, I should probably get on the bus before you get on the bus, okay? You can get on the bus that departs at X minutes if you arrive at Y minutes where Y is less than or equal to X, right? So what that basically means is I can arrive on any bus that gets here during or after I get here, right? Which is also intuitive, right? If I show up, I can't get on buses that already arrived and have left, right? Because when the bus arrives, it leaves, kind of. I guess that's the idea here, right? So if I arrive at time 10, either I can get on a bus that's at time 10 or any bus that comes after that if I wait for it, okay? So I can't get on a bus if it arrived before me because that basically means that I missed it, right? So the minimum time the bus can arrive is the same time that I arrive or after, right? I can't get on a bus that came before. That's equivalent to me missing the bus, right? And the bus is not full, right? So I can only get on that bus if it arrives either when I arrive or after, and the bus isn't full, meaning that, you know, there aren't people in front of me that get on the bus and, you know, make it difficult for me. And that'll make sense when we walk through a little simulation here. More formally, when a bus arrives, either if there's capacity or few passengers waiting for the bus, they will all get on the bus, or the capacity passenger will earliest arrival times will on the bus, right? So the arrival, if, you know, if we're in this scenario here, right, let's imagine that the capacity was 4, and there's these 3 people waiting in line already, and then there's a 4th person, and then this really tall guy, right? This tall guy's not going to be able to get on the bus because these 4 first will get on the bus, right? All this is very intuitive, right? These 4 will get on the bus, and now this tall guy will be the first one waiting in line, all right? Okay. The capacity passenger, okay. Return the latest time you may arrive at the bus station to catch the bus. Okay, so here's where the greedy approach comes into play, right? Because the latest time. So it's like, when is the last moment I could bring someone in and still give them an opportunity to catch one of these buses that's departing, right? Because it's possible that if I show up too late, I'll miss the last bus. And then when I miss the last bus, because either I show up too late or I show up so late that I get in line and I don't catch the bus, right? Imagine that this was a situation that was already been began processing. So, you know, this bus started carrying people, and then this bus arrives, these 4 get in line, and now this guy's in line, and then there's no more buses. In that situation, this guy wouldn't get the bus, right? But if the tall guy, I keep saying this guy, which makes it very confusing, right? If the tall guy arrived, if the tall guy arrived before this guy, right, he would be able to get on the bus, right? Because then these 4 would. So he could arrive later than these 3, right? But he can't arrive later than this guy. He won't get on the bus. So basically, you're trying to find a spot like, where can I fit this one unique guy in such that he'll have the opportunity to ride the bus, right? And what's the latest I can do that? Because of course, the earliest time I could do it is if I just arrive first, right? And this is always a fun game that we play when we wait for things, right? Like, I don't want to be the first one there. Like, I definitely could get there as early as possible and be the first one there and guarantee that I get in. But I don't want to wait in line forever or wait for the bus forever. So what's the latest time I could get there such that I will get on the bus and I don't have to wait? You know what I mean? So this is the kind of problem that, you know, is very intuitive and it makes sense. Like, it's a situation that we've all been in before, which is like, I don't want to get there too early, but I don't want to get there so late that I miss my chance. So the best thing would be is I get there as late as possible, but still get in, right? Have your cake and eat it too. Okay. So note that the arrays, buses, and passengers are not necessarily sorted. So this already reveals to you that we have to sort, right? So that's where that first case comes in, right? Because we need to like figure out who gets on the bus and when and where and when the buses come. So it needs to be sorted so we can process them accordingly, right? I need to know like who comes next, when's the next bus come, when are they going, right? That idea is very intuitive, right? When does this bus come? When does this passenger come? Will the passenger meet the bus? Will they not meet the bus? Who comes after that passenger? Because that will be the next person in line, right? So it makes a lot of sense that this system needs to be sorted in order to process it. Simulation makes sense because we need to figure out like who gets on the bus, who doesn't get on the bus, where will they be in line? You know, what does the situation look like as we walk through this scenario, right? So the simulation part makes sense because we might want to simulate the actual process of, okay, this passenger gets on the bus, the next passenger doesn't, they're waiting, then the next bus comes, then this passenger gets on that bus, then the passenger after their space, so they get on the bus, you know, and there's kind of that simulation component. And also, the greedy approach comes in where it's like, I'm trying to find the last moment, right? That's kind of like a greedy idea. It's like, what's the last moment I can get it? So I simulate. I figure, okay, this person can go on. So if I greedily decide to put my unique passenger in right before this guy, he'll get on and he'll end up on the bus. So that's where the greedy approach comes in. So that's kind of like a very hand-wavy, you know, explanation of why these 3 concepts are involved here. And just to summarize, right, we have to sort because we have to have things happen in order so we can understand who gets on the bus, who doesn't get on the bus, when does the bus come, who's the next person get on the bus. We have to simulate to figure out when does this person get on the bus, what does the scenario look like, and if we have that simulated information, we can greedily determine what's the last opportunity to get somebody on the bus. Okay. So if none of that makes sense, let's go ahead and just do a little bit of a simulation here and see if that helps us. Okay, so we have buses, and now I'm gonna, just for the simulation, with capacity 2, I'm just gonna draw boxes for the buses. Okay, and they arrive at, I didn't want to use that weird pencil thing. We have buses that arrive of size 2, so I'm gonna draw a block size of 2, meaning that, you know, each of these little squares represents the location that someone can go. And they arrive at 20, 30, and 10, okay? Now, the first thing I'm going to do is make sure that this situation is sorted, right? So if we kind of thought of this as like a, not to scale, right, but this was like a timeline here. The first bus that's going to arrive is at time 10. We'll draw that up here, actually. Let's draw a different color. So this bus arrives at time 10. The next bus will arrive at time 20. And the next bus will arrive at time 30. Let's just keep it. It's not the scale again, but, you know, I can at least make them, you know, equally distant from each other because they're, you know, 10 away each one. Okay. Now, our passengers arrive all over the place, right? So if we think of this in terms of when the passengers arrive and when the buses arrive, I'm going to kind of put people in the appropriate place so you know, like, okay, this person arrived before this person and this person and this person, right? So, you know, you have 19, 13, 26, 4, 25, 11, 21. That's when the people arrive, right? So the first person arrives at 4, okay? So I'm going to draw a circle for the people. So this first guy is going to arrive at 4, and he's going to be waiting for a bus. The next person arrives at 11, right? That's why this is important. Does it make sense? A little more sense now? Because, like, I need to know when people arrive and what bus they're going to get on, right? Like, 11's never going to catch this 10 bus, and 11's going to come after 4. So if 4 doesn't catch a bus, then 4 needs to get on the bus before 11. So it makes sense why you need like a simulation. You need the system sorted to know where things go. 4, 11. The next person arrives at 13. 4, 11, 13, 19, 21. Again, this is not scale. I'm just trying to put people before the bus that they arrive at. Why did this turn black? Isn't that crazy? Is it bugging? Nothing a little drawing can't fix. All right, so we got 4, 11, 13, 19, 21, 25, and 26, okay? All right, now we can already see some problems here with the way that this is because there's 3 people going to be waiting. There's going to be 3 people waiting here at least, and this bus can only account for 2, right? So there's already situations here where we need to consider, like, this person's coming before this person's coming, etc. Okay, so we got people coming at 4, 11, 13, 19, 4, 11, 13, 19, 21, 25, 26. There's 3, 6, 7 people waiting. 1, 2, 3, 4, 5, 6, 7. Just making sure I'm, dot my I's and cross my T's. So how is this going to work in the simulation? Well, 4 is going to arrive first, and then 10's going to show up, and I'm going to duplicate this. And 4 is going to get on this bus, and then it's going to be on its merry way. Okay? When 20 arrives, who's going to get on the bus first? Remember, it's first come, first serve. So even though 19 is like closest in this graphic, who showed up first? Well, 11 showed up, right? And 13 showed up. And they're going to be going on their merry way. And now 19, 21, 25, and 26. 19 showed up before 20, right? So 19 showed up before the 20th bus, but they were unable to get a spot because, well, unfortunately, there were other people in line. Okay, now when 30 shows up, right, 19 has been waiting for a long time, so he's going to get on first. And then 21 is the next person that's going to get on the bus. And then 25 and 26, well, they're just, there's no opportunity for them to get on a bus today. And this will be the scenario. Okay. So that's a hand-wavy kind of drawn-out simulation, which, of course, isn't going to work in code. So we need to think of a way of how can we capture this idea of, like, we're processing people, we're processing buses, how do we have wait, who's waiting, who's not waiting, right? That's the kind of thing that's kind of difficult about this problem, but it's a beautiful question because it really shows, can you program, right? Like, even I struggle with this a little bit because you kind of think of a, it's not always the most intuitive, the actual simulation part, right? So you need to think of a way to capture this where it doesn't become like a scrambled spaghetti code mess, but it still, captures all the conditions of the situation, right? And in this case, 25 and 26 aren't going to get processed. So when we look at the simulation now, it becomes a question of, well, where's the latest time that I could enter and get on the bus? So let's think of our, little green guy here. In this green guy, I'll put X. It looks like an Xbox or something, right? I'll put the X here and I'll say, where's the best spot for this X to go. Meaning, where's the latest time that I can place this X in this system, right? Where should I place this X such that, you know, this X will end up on a bus, right? Where do I put them, right? I can put them anywhere, and I have the simulation, and I have the initial scenario. Well, if I put X first, then I could put X before 4, and they would both get on this bus, right? So I could put X at 3, for example. Then they would get on the bus like this, all right? Well, I could also put X after 4, right, and before 10. So I could put X at like 10, all right, and then X would end up on this bus with 4. I'll actually put them in the bottom scenario. Right, if I put them there, then it would be on the bus here. Excuse me. Right, so I could put them on the bus there. If I show up at 10, I'll end up on this bus. So if I showed up at 12, right? If I showed up in between these two guys at 12, well then 13 wouldn't end up getting on the bus, and instead I would, but I would definitely get on the bus. You know, we can keep walking through this here. If I put them at 18, well, instead of 19 getting on the bus, then 18 will get on the bus. If I put them at 20, instead of 21 getting on the bus, 20 would get on the bus. If I put them at 24, well, at the 24 case, right, you'll notice here, he would then be stuck with the other people that didn't end up on the bus. Okay, so super hand wavy what I did right there. And maybe you didn't catch what the point is, but one of the conclusions you can draw from here is, well, you know, when I look at anybody, right, if anybody can get on the bus, I can get on the bus in their place, right? Sort of. Because I have to be unique, so I can't get in the same time that they do, but I could get in the second before them, right? So I can attach myself to anybody that gets on the bus and say, can I get on a second before them? Is there space for me a second before them? And if there is, I can take that space and get on the bus, right? So for 13, if I say, okay, 13 is going to end up on the bus. So anyone before 13 will still end up on the bus, right? So for anybody who's on the bus, anybody who ends up on the bus, anybody who ends up on a bus, anyone before them will also end up on the bus. Okay? So what I mean by that is basically the greedy thing here is, well, if you end up on the bus, right, if I simulate through the scenario and I say, you know what? You know, 21 ends up on the bus. Well, if 21 ends up on the bus, then you know who else would end up on the bus? Someone who showed up at time 20. So I'll just say, whoever the last person is that ends up on the bus, right? If I show up before them, I'm good to go, right? If 21 gets on the bus, well, I showed up earlier than 21, so I'll end up on the bus. So what's the latest time I can arrive such that I arrive before the last person that gets on the bus? That's what this problem really then becomes, right? It's what's the latest time someone can get on the bus? I'll arrive right before that. Right? Who's the last person to get on the bus? You. You're the lucky son of a gun who got here as late as possible and still got on the bus. So I'll just show up right before you and take your last spot. So I'm basically just trying to take the spot from the last person who gets on the bus, right? So the last person to get on the bus is this 21. So I'll just show up right before them at time 20. Right, now there's one more condition here that I'm not going to articulate yet, right? And it'll be clear in a second because there's one other kind of situation, but I'm actually going to let my code not error out, but there's going to be a wrong answer. And then from that wrong answer, we can determine what the other scenario is because there's one more condition in this problem that doesn't relate to this, okay? But basically, here's the idea, right? The main idea here is, well, I'll just greedily pick the latest position possible, which would be whoever the last person to get on the bus is, I'll just take their spot, right? And that's this 21. That's the last person to get on the bus. So what we need to do then is think of a way to capture this idea in code such that we can, figure out who the last person to get on the bus is and then just arrive right before them. All right, this 10 and 20 case, let's think about that really quickly. So passengers 2, 7, 18, so it's already sorted. So at 10, 2's there. There's capacity 2. 2 gets on the bus, and that's it. 17 and 18 wait before 20, right? The last person to get on the bus is 18 in this scenario. And remember, that has to be unique. So I can't show up right before 18 because then I would be conflicting with 17. So I have to show up before 17 and show up at 16. All right. And basically, just to really quickly write that out because I didn't realize this first example was a little bit more complicated, right? But when we have this 20 bus, right, the people that are going to get on it are 17 and 18. Oof. So 17 and 18. So when I bring this guy and you're like, well, you said before you go in before the last person. Well, the last person is 18, so do 17. Well, I can't because 17 is already utilized. So I'd have to show up at 16 to make this work, right? And then it would end up being 16 and 17 on the bus. So it's not always the last person because there are conditions where people show up like at one time, then the next time slot, and the next time slot, and the next time slot. So I can't collide, right? Your answer has to be unique. So it has to be 16 here instead of 17, right? Because this last person that gets on the bus, well, the person that gets there before them, 17. So we need a way to capture that within our code too, right? So that's another little kind of edge case to consider. Okay, so with that said, let's try to think about how we're going to actually write the code to make this work, okay? I'll actually just do it. Well, I kind of want that there. Those are the guys that are waiting. No, we'll do it down here. So I'm just, you know how it is. You're always trying to find a way to squeeze everything in because it looks good. Looks good, but then it looks bad. You know how it is. Programming. All right, so what are we doing here? So how are we going to simulate the situation, right? I think we have a general idea of how the code, of the idea of the high level concepts that are involved in this problem, but how do you actually write code that handles this situation? Okay, and I'm going to show you how you do that. Okay, it's pretty simple, not really, but this is one approach. There might be better approaches, but you know, this is actually the core of this problem, right? If I was interviewing you, this would be the core concept that I care the most about, right? Like, it's cool that you understand data structures and algorithms and little tricks, but to me, what's really important is, can you actually program, right? When I give you a scenario, can you simulate the scenario in code clearly, right? That indicates to me that you can do day-to-day tasks, right? Because a lot of these other concepts, they're not really day-to-day tasks, okay? And that's a personal thing. So when we have buses 20, 30, 10, the first thing we're going to do is sort everything. So, you know, we're going to do buses, sort, and we're going to do passengers, sort. I'm not going to spend too much time on this, but, you know, that's what we're doing, right? We're sorting both of these things. Hopefully that makes sense. Okay. So what we'll end up having is buses at 10, 20, and 30 after we sort. And we'll have passengers at 4, 11. Okay, let's just go up so we're not playing this game again. 4, 11, 13, 19, 21, 25, and 26. 25 and 26. Okay. So we need a system where we can process things as they come and then keep track of people that are waiting and etc. Okay, so what I'm going to do is I'm going to say, okay, I'm going to have a pointer P that represents the passenger that I'm looking at. Okay, and a pointer B that represents the bus that I'm currently looking at. Okay, and then I'm going to have a current capacity for that bus. Right, in this example, it's 2. Okay, so my capacity for the bus is 2. Okay, now anybody who arrives before me while I have capacity will get on the bus. Okay, so what I'll say is this person at 4. So if there's capacity on my bus, so the capacity is greater than 0, so there's still space on my bus, and the person I'm looking at is less than or equal to the bus arrival time, meaning that this person, make that red to match the color of the right? If this person, this passenger, sorry, can get on the bus, meaning that they showed up before this bus arrives and there's space, well, what am I going to do? I'm going to say that, you know, the capacity of my bus, I put capacity B, capacity of my bus minus equal 1, and I'm going to process the next passenger plus equal 1. I don't know why I chose yellow. That is literally the worst color that this could be. So I'm going to say passenger plus equal 1. All right, so I'm basically saying, all right, I'm still on this bus. I can process this passenger, right, with the capacity that I have, and I'm going to move over to the next passenger. Right, now this isn't going to be an if, it's actually going to be a while, okay? Because I'm going to keep doing that until what? Until I find a passenger that's greater than this bus, right? This 11 passenger isn't going to get processed by this bus because this bus is going to arrive at 10. It's going to pick up 4 and say, I'm gone. And then this person's going to arrive at 11 like, what's up? And there's not going to be a bus there. So then what we'll do is when this condition is over, we'll go to the next bus. So we'll increase the bus like this. So then we'll look at the next bus. So what we might as well do is we could... So how are we going to increase the bus after we consider all the passengers? Well, we could do that by saying this. So we'll say for all the buses in buses, right? So we'll basically increase the bus. We'll process until we can't process because we reach a person that isn't able to get on this bus, and then we'll increase the bus. All right. So now our bus capacity again is 2 because we're at a new bus. And then we say, okay, 11. Yes, 11 can get on this bus because there's space. All right, we're looking at this saying, we're saying, wow, the capacity of the bus is greater than 2. Yes. And the passenger on the bus is less than or equal to B. Yes. We subtract 1 from the capacity of the bus. Right, so now we have 1 spot left on the bus. And we increase P. All right, same case. Do we have capacity on the bus? Yes, it's 1. Is the passenger arrived before the bus arrives? Before or during when the bus arrives? Yes, it arrives at 13. The bus arrives at 20. All right, so the capacity of the bus goes down by 1. So now we have no more space on the bus. And we increase P. All right, now we get to 19. And we say, okay, we have capacity. Do we have capacity on the bus? No. And is there... We don't have capacity on the bus. Sorry, I did this problem actually differently, and now I'm seeing it this way, and I'm mapping it out, and I think there's actually a better way of writing it out. So it's kind of funny how that works, right? So I say, okay, actually I can't process 19, right? I can't process 19 because even though they arrive before the bus, right? There's no space left on the bus, right? There's no space left to process this person. So we have to wait here now. So with that, we would increase B again, right? And we'd say, okay, now that we've increased B, our capacity starts over again, right? We have a brand new bus to fill up. We say, can 19 get on the bus? Yes, 19 can get on the bus. 19 is less than 30, and there's capacity in the bus, so this goes down to 1. We increase P. We say 21 is 21 less than 30. Yes, it is. Is there capacity on the bus? Yes, there is. So this goes down to 0. Right? So then we go to 25. We say, is there space on the bus? And there's no space on the bus. So we increase B. We get to the end. And of course, that would be a clear... This is kind of a simulation without considering the greedy part, right? Of course, we have to sort buses first. You know, buses sort. In passengers sort. But this is the sorting component and the simulation component in one, right? This is the simulation code to simulate this scenario, right? Now what we need to do, I'm going to delete this because I want to have a good thumbnail. And this is just wasting space and it's terrible writing. So it's kind of like, terrible in multiple capacities. And we'll move this code up. This is more of an intermission here, guys. I apologize for doing this, but I just like having everything nice and compact and and clear so we can kind of see everything here. All right. But I guess the only component of this now, right, is, well, you know, how do we figure out where we put this green guy, right? Where are we still got to put this guy somewhere and figure out where that guy goes, right? And basically I said is every person that ends up on the bus, we can try to put someone right before them, right? So if we can put this P guy on the bus, we can basically say, well, I'm going to put this P guy on the bus. So before I do any like the work here, I'm just going to ask the following question. I'm going to say, all right, if I put this guy at P on the bus, can I put my green guy on the bus in his position, right? And not in his position, but right before him. So I could say, well, I can put him on the bus if what? If, this is where it gets a little weird, okay? Now this is a P and this is B. So B is actually a pointer and P is just B is the actual person at the bus and P is the location. So this P thing isn't actually the correct code here, right? Because P is just the pointer. We want the passenger at the pointer. Okay, and the reason why that's important is, well, because B is the actual bus value, because we're looking at each of the bus values. P is just the pointer, so we want the passenger at the pointer. So where would be the best place to put this new thing, right? When we're looking at 21 and 21 gets on the bus, the best place, that would be passengers of P, right? Passengers of P equals 21. So the best place to put this person would be passengers of P minus 1, which equals 20, right? But I can only do that if there isn't 20 within this array. And if 20 was in this array, where would it be? Well, it's minus 1. All of them are unique. So the location of 20, if 20 was in this array, would be passengers of P minus 1, right? If 20 is not in the system, but if it was in the system, where would it be? It would be right here, right? So all we got to do is say, can I put this thing at spot 20? Well, I can only put this thing at spot 20 if there is no 20 in the system. Where would 20 be? It would be right before me. So if passengers of P minus 1, right, at the previous location, if it doesn't equal passengers of P minus 1, right? So passenger of P is 20. So passenger of P minus 1 is 20. So if 20 was in the system, it would be at this location. So if these two things aren't equal, then we can put our guy in that slot. Okay, so if that's the case, then we're going to put our little red X guy to passengers P minus 1. Okay, so that's pretty much it. That was super confusing and terribly written, but hopefully when I write out the code, it'll make a little bit more sense and it'll be a little clearer what I'm talking about here. Okay, so the first thing we have to do is we have to sort buses. The next thing we have to do is we have to sort passengers. And then the next thing we have to do is we have our passenger here starting at 0, our index, and then we're going to look at each buses. It's literally the same thing I wrote, right? That's the beautiful thing about Python. It's pretty much pseudocode. For B in buses, we're going to say, well, while the capacity of the bus, right, is the total capacity. And we're going to say, while the capacity of the bus is greater than 0, and the passengers that arrives here, well, we should keep a track of, make sure we don't go past passengers. So is less than the length of passengers. So this is just a condition to make sure we don't go outside of the array. If we process all the passengers before we process all the buses, we don't want to get an error because we've gone outside the boundaries, right? And P is less, passengers at P arrives, so they arrive before this bus. Well, then we can do the following, right? We're going to do res as our solution, which represents the time that this bus can, the person can arrive, right? That little red X, that blue, green X. We're going to say, okay, we're going to play first this game. We're going to say, well, this person can arrive. This person is going to get picked up if we're in this scenario. So that means passengers at P minus 1. So we can put them right before this person. Only if passengers P minus 1 doesn't equal that. Or they came at the same time, so I can't put them, right? Like here. Right, in this scenario, when 18 arrives, I can't put my guy at spot 17 because there is a 17, right? So 17, 18, 18 minus 1, 17. The previous slot is 17, so this wouldn't fit, right? What the hell is that? Oh, I got a new Mac and it does some weird stuff. Okay, if passengers P minus 1 not equal passengers P minus 1, this is now our best case, right? This is the best place we can put this person now. And it's in the previous slot. And then we start doing our accounting. So we process this person, so we do P plus equal 1. And since we process this person, there's one more person on the bus. And we're getting an infinite loop here. Time limit exceeded. What did I do wrong here, guys? All right. How embarrassing. Okay, because that's only for that. So this is only to figure out if the person can be processed. Well, that's not going to stop the system from going through, right? We're just trying to figure out where we can put someone. And if it doesn't meet the scenario, then we can't put them there. That's all that means. All right, so this code looks pretty clean, and it makes us think, oh, we're probably done, right? We probably finished with this. Well, let's submit it, and we're going to see a little scenario. Throws a little wrench in this, and then we'll consider what that represents. Okay, so let's look at this problem here. And probably in an interview, this wouldn't be a good sign, right? Because you didn't think of all edge cases. But sometimes I feel like it's better in videos to just kind of explain a core concept, run through it, explain the edge case, work in the edge case, right? Integrate that in. Right, but in this case, we have... we only have one bus, right? So it's a weird scenario here, right? We have one bus that arrives at 3. Now I'm going to keep these colors consistent because I messed up. Okay, so we have one bus that arrives at 3, and it has capacity 2. Okay, so this bus arrives at 3. I don't know why it's so hard to do this. This bus arrives at 3 with capacity 2. And then we have people that arrive at 2 and at 4. So we have a person that arrives here and a person that arrives here. Okay. Now I'm saying that the answer is 1, right? But the answer is actually supposed to be 3. And why is that the case? Well, when this person arrives at 2, I could say, all right, I can come right before this person comes. So I could make my guy arrive at 1. So I'll make my guy arrive at 1, right? And then they'll get on this bus together, right? And then when this 4 comes, well, the 4 is never going to get processed, right? Because the only bus comes at 3. This person arrives at 4. Sorry, better luck next time, right? This 4 is never going to be processed, okay? But what's interesting is the answer is 3. Well, what does work here, right, is, well, if I put 3 here, then this guy can end up on the bus. Because the situation we're still not accounting for is, well, yeah, we can come before anybody who gets on the bus. Or if the bus arrives and there's still capacity, we can kind of sneak in, right? So the thing we're not considering is the situation where, you know, I can actually get on this bus by being there when there's space and there's no one waiting in line. Okay, so it basically, if I process all the people waiting for the bus, right, and there's still space, I can occupy that space, right? So if I've processed everybody and there's still capacity, then I can go in at that capacity. Right? The time that I can go in is at that time when that bus arrives. Right? So I can go in at the very last minute, right when the bus arrives, when there's nobody waiting. Okay? So basically what happens here is I say, well, if there's still capacity at the bus, right? So I've processed everybody that can be processed here. And the only kind of other situation you have to think about is if there's capacity of the bus, and this one's kind of like it's kind of tricky. I'll explain it in a second. Right, because the last person I processed is passengers P minus 1. So that's the last person that's on the bus, right? So it's possible that they arrived when the bus arrived, right? So basically, if this was instead 3, right? If this was 3, this person could get on the bus. But I couldn't then make myself 3 because there can't be, I mean, everything has to be unique here, right? So I can't make myself 3. So I can only make myself 2. So then should I make it well, if 3 was processed, then I would have already considered making myself 2, right? So that's why this greedy approach always works. Like I ask this greedy question every time I process someone just to ensure that I always account for all possibilities, right? Because here I can't put it at 3, even though there's capacity, I can't put it at 3 because there's already 3. So I'd have to put it at 2. Well, if I put it at 2, I've already processed it when I processed that 3, okay? And P minus 1 is the last person that I process. CP, why do I keep putting CP? CB, capacity of the bus. Not capacity, CP capacity. All right. Oh no. All right. So we're getting a weird error that I didn't expect, so now I'm scared. All right, so there's a bus that arrives at 3. All right, sorry guys, I'm thinking out loud here. Thinking out loud. I'm thinking in my head, as you should. All right, so what do you do when this happens in problems? You panic and you quit. No, you need to start doing a little bit of debugging, right? So what is my res here? Okay, so so what is my res at each scenario? Right, so there's only one bus, so I should only get one res, unless res was updated here to B. Res should not be updated to B here because I do use all of the people to get in the bus. So it thinks res is 1 here. What's my capacity of the bus here? Right, so sometimes you can just start dumping variables. So it thinks I have 1 person left in the bus. Why is that? Okay, because you can arrive at the same time, right? So passengers P less than or equal to B means that they arrive at the same time, right? They can arrive at the same time, right? And I think I put that here, right? Less than or equal to B, not less than B, right? Less than or equal to B, they can arrive at the same time. And we cry. Okay, cool. So let's actually make this a little shorter so we just feel so smart about ourselves. Wow, we're just so smart. We're so smart because we can make our code super short and super unreadable. All right. All right. All right. All right. All right. Okay. So what is the run and space complexity of this problem? Okay. So time, space, and we'll say that we'll keep consistent with the system they had here. So let's say n is the length of buses and m is the length of passengers. All right. For time, we have to sort buses. That's going to take big O of n log n time. To sort passengers, that's going to take m log m time. We're going to look at all n buses. And then, you might say, like, okay, there's 2 loops here, so that's n times m. But, the way that this works is, like, we only increase in one direction, right? So even though there's 2 loops, like, I'm never going to go over a whole system over again, right? Like, I'm only increasing one, then I'm increasing the other adjacently. And they'll never be ahead of each other, right? And they never go back. So even though this is a loop inside of a loop, right? there's gonna be n things and at most m things, right? Because I'm just increasing this thing once, and I'm basically increasing all the buses once and all of the passengers once. I'm never going over anything again, right? So I'm gonna go through the whole bus array and at worst the whole passenger array, right? So that's gonna be n and then m, not n and m, but it's gonna be all of n and all of m because you only pass through each thing once, right? So this whole thing will only go through all n buses, and this whole thing will only go through all m passengers. So that's n plus m time, right? And well, this is bigger than n, and this is bigger than m, so these get overshadowed by these operations here, right? So these go away, okay? And then these are constant operations within them. Update this, return res. Okay, so for space, this is technically could be O of 1, right? Because this sorting algorithm with like a heap sort has n log n runtime and can be constant space. So these could both be constant space algorithms. Maybe they're not in Python, but we could build a heap sort algorithm, in place heap sort, have n log m time, whatever, and it would be constant space. 2 variables, so independent of the number of things we input, we create these 2 variables, we create this 3rd variable, we just update them accordingly. We're not creating any new things, doing anything special here, so that's just O of 1 space. Okay, guys, hope you have a beautiful rest of your day. I hope this was a little bit helpful. It's been a while since I've been able to make a video because my last computer failed on me, so I bought a new one. That's why you're seeing me through this new feed. I basically connected my iPhone to this camera feed. The integration of the Apple ecosystem is very impressive, even if I often find the software a bit buggy, problematic, and just aggravating. The ecosystem is definitely one of the major benefits, right? I got my iPad connecting automatically to my MacBook, which then streams a video feed directly from my iPhone, right? That's something that would be pretty difficult in a Microsoft space, and this is all just using default, out-of-the-box Apple applications. All right, guys, peace out. Hope you have a beautiful rest of your day.